Assalamu alaikum wa rahmatullahi wa barakatuh. This is the second video of Chapter 8, Newton's Laws and Applications. At the end of this video, you're going to be able to state and apply Newton's third law between two interacting systems, state and apply Newton's first law on a system. First, let's remember what we took in the first video. We said that a force can be represented by two components, one along x and the other along y. We should distinguish between external forces and internal forces. Newton's laws of motion. We have mentioned in the first video that we're going to use Newton's laws to study the motion of an object. What are these laws? First, law of inertia, the fundamental principle of dynamics, and the third law of interaction. We're going first to explain the law of interaction. This law states that to every action there is a simultaneous reaction equal in magnitude and opposite in direction, such that force exerted by A on B equals to the opposite of the force exerted by B on A, so that it is interaction between two bodies. Let's consider a real-life example. Consider a spring. If you press a spring downward by your finger, it is clear that the finger exerts a force downward on the spring simultaneously, and in opposite direction, the spring exerts an upward force on the finger. We say that simultaneously there exist two interacting forces between the finger and the spring. Thus, the force exerted by the spring on the finger is equal to the minus the force exerted by the finger on the spring. It's clear that forces always exist in pairs. Another example, a fish. Consider a fish that moves forward in water. Two interacting forces exist simultaneously between the fish and the water, and we say that F of the fish on water equals to minus F water on fish. As we said before, forces always exist in pairs. Let's try to solve an application. Consider these figures. In each of the figures above represent, not to a scale, the forces of interaction between the two interacting objects. Please pause the video and try to think of it. Okay, considering the first figure, we can see that the man is trying to push the wall to the right. Simultaneously, at the same instant, the wall exerts a force on the man to the left. So we draw them opposite in direction, but of equal magnitudes. The other example, we have a book exerting a force downward on the table, and at the same time, the table exerts a force upward on the book. So they are of equal magnitudes, but opposite in directions. Now we can move to the Newton's first law, the law of inertia. But what is meant by inertia? Galileo was the first to talk about inertia. Inertia of a body is its resistance to any change in its velocity, magnitude, and direction. In other words, objects tend to keep on doing what they are doing. If objects at rest, they prefer to stay at rest, and if it's in motion, it prefers staying in uniform rectilinear motion with constant velocity, magnitude, and direction. It's good to ask a question. Do all objects have the same inertia? Well, not really, because inertia tells us how strong an object's tendency is to resist change in its state of motion. Think of it like this. Suppose there is a large, heavier block put on a table next to a relatively smaller and lighter block, which one do you think would be easier to push? The tiny block. Good. But why is that? It is because the heavier block's tendency to resist the change in motion is more. Inertia of an object depends on mass of the object. The greater the mass of the object, the greater is its tendency to resist the changes in its state. So, if we apply equal forces to both of these blocks, the tiny block will move easier. In our words, in physics, it means faster or greater acceleration. That means, in this case, it reaches a greater speed in same interval of time as compared to the larger block. How can we relate inertia and mass? We have said that inertia is the tendency of an object to resist the changes to its state of motion. As a result, inertia is related strongly to the mass. Then we can consider that the mass measures the inertia in translational motion. What is the law of inertia then? Since we have said before that a mass tends to resist any change in motion logically, said it cannot change its motion by itself. Therefore, it needs an external intervention to make this change. Which is what? It is not more than the force. Consider the ball that rests on the ground. Would it move by itself? Of course not. It needs an external intervention from a boy, for example, who is going to change its speed. After that, it hit a rock. What happened then? The rock changed the direction of motion of the ball, thus a change in motion. Finally, the boy stopped the ball and also changed the speed of it. In all these three cases, the ball is acted upon by unbalanced forces. We come to an end that objects continue to do what they are doing unless acted upon by unbalanced forces. To make conclusion about the first law, when we have balanced forces where sum of forces is zero, either the object was at rest and it will stay at rest, or if it is in motion, then it stays in uniform rectilinear motion with the same speed and direction. It is good to discuss a sample problem. Here we have a truck carries a pile of food by means of an inextensible rope where they are held at rest. Given the mass of the wood, 300 kilograms, find the tension in the rope and use G equals to 10 meters per second squared. In solving problems about a system at rest, it is good to remember the equilibrium of a body that is taken first in grade 9. But this year we're going to use projection of forces along the axes X and Y. First step to solve the question is to define the system, which is the pile of wood. Then name the forces, which are good, the weight and the tension. According to Newton's first law, sum of forces equals to zero in vector. Why did we mention first law? Since we are talking about a system which is at rest. So it was at rest, it keeps at rest. It is the first law of Newton. Now, the forces are mg vector plus t vector equals to 0 vector. The weight is vertically downward opposite to the positive y-axis. So its projection is minus mg. And that of tension is just t, since it is vertically upward with the positive y-axis. So we make calculation and we find the magnitude of the tension is 3000 newtons, and the answer should be positive. Another real-life situation, the car accident. One of the safety devices in a car to protect you from the effects of inertia is the seat belt. When the front end of a car hits another object, the car will suddenly stop or slow down because of inertia in your body. You will want to stay moving at whatever speed it was moving before the accident. If you are not wearing a seatbelt, this means you will hit a windshield. The seatbelt provides a force to stop your body's motion. Physics then advises you to wear your seatbelts in the next time. Before ending, it's good to mention a misconception that happens between Newton's third law and Newton's first law. Two balanced forces and interaction forces are not the same. Two balanced forces always act on the same object. The chair pushes the person upward and the gravity pulls the person downward, while interaction forces act between two different objects. A chair pushes the person upward, where the person simultaneously pushes the chair downward. With balanced forces, we have two external forces acting on the same body, who is the person. These forces are the normal and the weight, and their sum is zero. While in the other case, we have interacting forces between two systems. These interacting forces are opposite but equal in magnitude. Usually we aim to study the motion of a system, so we have to find the sum of forces acting on this system, and it is not useful to add forces acting between two different systems. It is enough for this video. Just remember that we have talked about inertia, the mass, Newton's first law, and Newton's third law. This is the end of part 2. Study well, and thank you for watching.